Beep.
Yes. What can I do for you?
4.5.
It was the same question.
I knew it.
Excellent.
I have an idea of how to do it, but
Okay.
I'm not sure if that's the right
All right, let's take a look.
Okay, so it's f of z equals z plus z conjugate,
Oh, yeah.
and we have to integrate that over a circle, center 0 and radius 2.
Yeah. Okay. Cool.
Okay,
Yeah. So what do you?
so in one of our lectures, I remember you saying like if we have a function f of z and it has like a real and imaginary part, we have to do like integrate a to b, like h of the real part plus I h of the imaginary part, and then divide that.
Yes.
And I was thinking maybe we have to do that because not lambda, the thingy, I forgot what that's called.
Circle.
No.
Conjugate.
Yeah,
Gamma.
yeah, whatever.
Gamma. Okay. Yeah.
Gamma, yeah.
Yeah.
That I can express as 2 cosine t plus 2 I sine t. And we can say that that's h of t. And then we could just do z as h of real and then h of imaginary, and z conjugate as h of real minus h of imaginary. And kind of go from there. But I'm not entirely sure.
That all sounds like right on track. Noah, what was your trouble with it? Just
Just the fact that this was a real function, and I was like, it wasn't a function I knew how to deal with.
okay.
honestly.
Cool. So let's go. Like for this one, is this function differentiable? Is this function differentiable anywhere? Just the z conjugate. So if I gave you this, is that holomorphic anywhere? Yeah, that's a pretty mess. How do we know that?
The Cauchy Riemann.
Yes, exactly. So this is x minus iy, this is our u, and so our u is x, and our v is negative y. And then when we do u with respect to x, that's 1, v with respect to y, barf immediately. So that thing isn't differentiable anywhere. So a lot of the results that we talked about toward the end of the class don't apply. Because you might want to think, oh, let's see here. So let's just do this. 0 to 2 plus c conjugate dz. You might think, oh, it's a circle. This doesn't blow up anywhere. There's no division by 0, so the answer is 0. But I don't think that's going to be our answer here. So what we're going to do is we're going to use this version of things. If I want to find complex integral over a contour, and I'm just kind of naive about this. I don't really know anything. I just need to compute it because I don't see holomorphicity or anything like that. So this is just going to be integral a to b, which is the parameter range for gamma. So we have gamma of t is defined like so. And then this is f of gamma of t, gamma prime of t dt. So that's what we're going to do here. So we're literally going to find a parameterization, which maybe you did. So we've got gamma, and I think you actually said this, Avina. So we've got 2e. Yes, ma'am, absolutely. That. So then this becomes integral, and I'm just going to get it set up because I don't want to give it all away. But so 0 to 2 pi. And then we're going to have 2e to the it, that's the z. And then what's the conjugate? Negative it, exactly. So plus 2e to the negative it. Times gamma prime, which is what?
Just 2i e to the it.
2i e to the it dt. So I just need to crank that integral out. It sounded, yeah, I didn't want to say that. I was like, this is way too complicated, but I appreciated your thought process. Noah, does this, yeah. So when all else fails, go here. Can't really go wrong with it. Other questions on the homework?
Let's see.
You good, Lou? Olivia, you feeling okay? Yeah. And I should ask Grace just to be complete. You're good with, yeah, okay, cool. Yes, ma'am.
Could you just check if I turned this into
Turn.
like the formula in f of z over z minus w, if that I converted that properly.
It seems like you rewrote, is there a squared there or not? Because there's no squared there, but there's a squared there. I think you should check this. I think you should check that first.
Probably.
And then let's touch base right after class, okay?
Okay.
And yeah. Other questions? Things you want me to look at? Okay. Cool. Here's a warm-up problem. Warm up.
And I can't just use the fact that that should be 0, maybe, right?
Say that again. Say.
I can't just use a simple trick on that. To
So
make
what
it
would
say-
be the trick? Let's talk about that.
It's, I would maybe, no, it's not differentiable, so I can't use the trick.
That's right.
Okay, okay.
Yeah, it doesn't have an antiderivative.
Yeah.
So yeah, and we can't use those methods. So it won't. If it doesn't have an antiderivative, it's
Right.
cool. Let's see. I think I might actually give you another book for the series. I don't know if I like what this book does. I mean, it's a free book, so there's that. But I think there's better presentations of it, so I'm going to create a PDF and get that to you to start looking at. I think there's much better ways to talk about series. So, my friends, how about this one here? We've got the integral of the arctangent of z, oh shit, over z minus 1 around the curve gamma, and gamma is defined by this ellipse, so it's a counterclockwise traversing of this ellipse right here. This is a good warm-up because you got to pull a bunch of shit together. So, where is a problem for this integral?
1.
1. What results are we going to use here, and what do we need to check? What formula are we going to use? Whose formula?
That f of z over z minus
Cauchy.
w.
Who is that
Cauchy.
guy? That's Cauchy, yeah. So we want to use Cauchy's formula, so let's just recall that. That is the integral on some circle, but we can have any curve here. And let's see, then we have f of z over z minus w. This is the basic version of Cauchy's formula, is 2 pi I f at w. So, this curve gamma has w on the inside. The basic setup here is that gamma is a counterclockwise oriented curve and w's inside. The thing on top is holomorphic, is differentiable in a region around gamma. So there's no holes, that thing doesn't blow up, it doesn't have division by 0, nothing like that.
Although arc10 might not be that. Because it would probably involve LNs, right? Since you're doing the opposite of ease.
Yeah, this is the thing I kind of wanted to discuss, indeed. Is arctangent differentiable? No. So if let's go back to Calc 1 real quick.
Please, I don't remember.
I was thinking of integration.
But we wanna just kind of think about derivatives for a second here, because we wanna see, is this thing differentiable? Do you remember what the derivative of arctangent is?
No.
Okay, that's okay.
I knew it was of the form 1 over something.
Yes,
But
that's good, that's
It
a,
is
that's
1
a move
over
forward.
1 plus x squared.
Yeah, yeah.
Is it square root of 1 plus x squared?
I'm sorry, what?
1 over square root of 1 plus x squared? Oh,
No, that's arc sine. And then arc cosine is just there's a negative on top. So we got that. This ring bells vaguely. It seems like the bells are like have been rung, but they're like we're checking in on them, things like this. So arctangent is actually holomorphic.
Okay.
So we're good. So it doesn't have any holes. There's no blow-ups. So what is my f of z here and what's my w?
F of z is arctan z, w is 1.
Mm-hmm. Thanks, Lou. What do I have to see? What do I need to verify to use this result?
That 1 is in the curve.
Yeah, that 1 is inside this ellipse. Please decide that for me. Let's find out. If 1's not inside there, what is this integral?
0.
Then it's 0.
Yeah,
Yeah,
because it's a closed loop.
exactly. So this thing here, the integrand, is not blowing up at all in an open region around the curve. No big deal. We're good. 0. Do we remember how to get some of these? Do we remember this?
Yeah.
Can you help me?
So all x between -2 and 2 is going to be in the ellipse.
Oh, that's good. So Noah's like replacing y with 0, noting that x would have to be between -2 and 2. What is the standard form for an ellipse? It's like, this is really what I wanted to talk about. Right? What does this tell me? If I know that I have an equation like this, what kind of an ellipse would that be? How far out horizontally? Yes, I heard A. I think it must have been Labina. It was so quiet. But I'm not sure, but I think maybe. And then the vertical is B, and then you have this ellipse. And so our ellipse is going to be traversed like that. We just got to figure out, is 1 in there? And kind of based on what Noah was saying, yes. But let's just convert this first. So this is x squared over 2 squared plus y squared over 1. Wait, okay. So if I divide that by that, because I want to get a 1 over here, that's a 4. So that's actually a 1/2 squared in the bottom. So this ellipse looks like this. Goes out to 2. Goes up to a 1/2. Obviously the scales are different here. But we know that 1 is right inside there. So what will this integral be?
2 pi I arctan 1.
2 pi I arctan of 1, yep. So this, what's arctan of 1?
Pi over 4.
Yeah, I like that, thank you. I just wanted to review some of these basic kind of facts for us. So pi over 2i. Does everybody get that? Because arctan of 1 is pi over 4. That's what, oh wait, so pi squared, right? Actually, yep, oops. Do I need to explain any of that? Sound good? Let's do another one. Several challenging problems today. That was kind of just the good old warm up, just to talk about some things that I like talking about. And gamma is a counterclockwise rectangle. So I'm going to plot out gamma for us. So gamma goes through 1 plus I over 2. And so what we're going to want is 1 on 1 plus, actually, I'll just do it one at a time. So the first point is 1 plus I over 2. The second point is negative 1/2 plus I over 2. This way, here's negative 1/2. Traveling that way. Let me get this labeled a little bit better. That's I over 2 right up there. And then we go to negative 1/2 minus I over 2. And then we move that way, just straight under that point over there. And so that is 1 minus I over 2. And then we come back up. That's our curve. Can you find that integral for me, please? This will take some time. There's some computation to be done. And we can use Cauchy's formula. That's what we're shooting for. I haven't actually done this, so I'm going to do it too. Bless you. What we're trying to see, if you're not quite sure how to go, is can we write it? Is there a place where that thing blows up inside that rectangle, where there's a 0 in the denominator? And if so, how would we rewrite it to match Cauchy's formula? If not, our answer is easy. Oh, yeah. Yeah, how come? Oh, yeah. Yeah. Good, good. Let me see if I can do it. So let's see. Let's actually do. Let's make the second one I was going to make. It's not on my paper, but let's see. So we want. What if we raise up the top of the rectangle, just the top of the rectangle, to a height of 2i? Yeah. So once you get done with this one, try it for this rectangle. The answers will be different. I'm not trying to be tricky here. So that's gamma, and then do it for this gamma 2, which pretty much is the same, except it goes up to 2i. But otherwise, all the points are the same. Come around and see how things are going. Did you get that first one?
Yeah, I think it's just
Yeah.
cool.
That's good. Yeah. The next one's not quite as lovely drawing. Oh, those look like Calc 3.
Yeah.
That's some serious Calc 3. Awesome. I'll let you know. What do you think? So what is the thing where, if this thing has a 0, if the bottom goes to 0, somewhere inside here, then we've got a problem and we need to like figure out using Cauchy's formula where that 0 is. But if it doesn't, then what's the answer? If this thing, it doesn't have 1 over 0 inside here, what will be the answer? Does that question make sense? Let me say it again. So if this 1 over z squared plus z plus 1 is analytic around inside that curve, then what's the answer? So if I integrate a function that's purely analytic and it doesn't have any infinities inside the curve, what do we get? This isn't helping me constantly doing this. So what are the good guesses for complex analysis? Yes. And when do we get 0? Yes. So if this thing is analytic inside here and just kind of on it or around it, then the answer is just 0. How could I figure out if this has division by 0 inside the rectangle? There you go, my friend. Quadratic formula. There you go. Yeah. And then that'll help with the second part as well. You did hear? Okay, cool. All right. I'm dying to kind of see what the other one is. Did you get it already? Really?
I think so.
Wow. Okay. Let me see. That's wild.
I'm thinking about it.
So let me see what you did.
I was like, it's actually just right here. At first I was like, oh, so it's gonna be 2 over this and then like that.
Yeah.
But then I was like, no, I don't have to do that because it already, so it's just 1. And no matter what you plug in, it's still just that 1. That's the end of the
It won't be this time.
No?
No. I'll show you. Yeah. Because you need to actually factor that polynomial.
Yeah, I didn't want to do that though.
You got to. That's
I
the
mean,
only
I
way to
found
do
the
this.
zeros.
Yeah, you've got the zeros.
By factoring
You've
it.
got the factorization.
But I didn't want to find like the a plus b.
Well, just take. So.
Isn't it just,
Well, here. So here's what I would recommend trying. I want to take 1 over z squared plus z plus 1 and write it as a factored thing, right? So z minus a, z minus b. If a or b is inside here, that's going to be the bottom part. So let's say that a is inside, suppose a is inside gamma.
Oh, but we didn't have to do it for the first one. Just
That's right.
Okay.
That's right. So your f becomes the other part of the factor.
Got it. Okay.
Does that make sense?
Yeah.
Yeah.
Wait, which one's inside gamma?
Yeah, I tried to make it so the, unfortunately the uglier one is the one we get to plug in, but yeah, they're all pretty ugly. Yeah, I agree.
but isn't it on?
I don't think so, is it?
Yeah,
Because we have negative 1/2 plus square root of 3 over 2i.
which would be on
Oh
the
shit!
line.
Yes, yes.
What
Move
happens
this. Yes,
then?
thank you, Noah. Yeah, thanks. Change this. Sorry, you're right. I should have changed that. Make it so there's only that top point inside there. That was what I was trying to do in my head, but I didn't do it very wisely. So let's just make this like this. Thanks for catching that. Good one. Yeah, if the problem is on the curve, we have to go to that original thing we talked about. So you want to, this is our factorization that we want to come up with. And the way to do that is just use the quadratic formula to find the roots, and then just z minus each of those things you found from that formula. There's only there's two places where this goes bad, at this number and at this number. This one is outside the curve. This negative 1/2 minus square root of 3 over 2, this is more than a half that we're subtracting off. So that one is down here somewhere. Let's see, like down here somewhere. But the other one, this one, is inside the curve. That one is right up there. So that's our W. And the rest of this function is the f of z. So I take that integral, and I'm going to rewrite it as the analytic part on top whoops, that's the minus part on top, right? Yep. So that's the part that's good inside the curve, and then I put leave the other part just underneath. And now I can use Cauchy's formula. This game we're playing, I just wanted to start this game today. We're going to learn some easier ways to do this in the future, but it's good to have several methods. So this is Z, this is my W. Just plug that in. I'll just put it all together. Let's see, so that's plus 1/2 plus square root of 3 over 2i. So this is 2 pi I square root of 3i on the bottom. I's cancel. 2 pi over root 3 is our answer. Yeah? Anybody else getting that?
Yeah.
Yeah.
That's what I got.
That is what you got. Cool. Should we talk about this more? I've got more in practice for sure, but that's the game. Mostly now you see the game that we need to play. It's looking for division by 0, identifying where that happens inside the curve, and then dealing with it using Cauchy's formula if possible. And I'm happy to talk about what I just did there. Would anyone like me to go through this again? Kind of give a grand summary, or are we good? Yes, ma'am.
We could do that either way, right? That we'll see.
We can't because, I'm glad you asked that question, Lavina, because if I had done this, like this number is not inside the curve, so the W wouldn't be inside, and this would be not holomorphic inside. So I have to, I keep the troublesome part in the bottom and move the non-troublesome part to the top.
Okay.
Does that make sense? Yeah. Cool. Let's see what else. Oh, see, I got that little sheet. I remember I was having a flashback to when I was a TA, my first TA gig, and I was writing my lecture on like envelopes or like, you know, piece of toilet paper, whatever. It was just like whatever I could find, I was writing.
I thought you were talking about you were going to have a lecture on envelopes for some reason.
No. That's it. Yeah. Maybe a Diffie Q. Envelope of a curve. But yeah, no, I came in, I was like a grub. Like now Amy makes me dress in nice clothes. When I met her, she started dressing me properly for a human being. And I would just come in with like whatever, and I got reported to the chair of the department. One of my students was not at all happy that their professor, I wasn't even a professor, I was just some dumbass like TA, wrote their lecture on a piece of paper like this. He complained that my lecture was written on an envelope, on the back of an envelope. Anyway.
You should have expelled him.
I should have, yeah. I should have expelled him from my mind, but apparently I haven't. So, unfortunate. All right, here's another one. Gamma's going to be a weird-ass curve again. But here we have tangent of z. Oh no, fuck that. No, I won't do that. Because there's part of that I don't want to deal with. So let's look at this guy right here. Clearly some factoring can happen in the bottom. So now the big question is, which of the 4 possible zeros are going to be inside the curve? So let's let gamma be the rectangle with these corners. And it's a counterclockwise rectangle with these corners. And it doesn't matter where you start. The corners are 1/2 minus 10i, 1/2 plus 10i. So this is kind of circuiting you around. Negative 1/2 plus 10i, negative 1/2 minus 10i, and then back to here. Let's see what we can do with this. Let's see if it creates any new problems for us. Or maybe life is really good and we don't have any problems at all and we just put a 0 down. Always hoping for the holomorphicity. The low-hanging 0 fruit. Step one, find the fourth roots of 1, which you know how to do. You get good amounts of sleep, Noah, or are you like a guy who doesn't get much sleep at all?
I can't sleep on not Mondays and Wednesdays.
Good, good, good.
Yeah.
Are you a morning person or a late
No.
night? You're a late night person.
Yeah. Late night's better.
Just if you start seeing anything weird here, let me know so I can intervene and help. Because there is something weird you should notice here. A shiny Bobo strawberry stuffed oat bite to the first person who tells me what's going on here that's new.
There's 2 boards.
Go. A little high there. There's two troubles in here. What are the fourth roots of 1?
1, -1, I, -I.
Yeah, exactly. Right, and that's something that we can kind of grok that by just drawing a picture. We know one of the fourth roots of 1 is 1, and then we know that they're equally spaced around the plane. We also know -1 too, right? We could have grabbed either of those. So the other 2 must be I and minus I. They both live in here. Oh shit. So here's what we're going to do. We're going to turn this into 2 problems. We're going to make this 2 Cauchy integrals, our 2 integrals of the form ready for Cauchy's formula, in the following way. So if this is gamma, I'm going to break gamma into a top half, gamma 1, that goes like this. So gamma 1, let me get a colored pen here to help with seeing this. Gamma 1 I'll do in green. And I'm just going to have it cut straight across the real axis there. So gamma 1's counterclockwise looks like that. Gamma 2 looks like, it's keeping the same flow down here. So remember this was like this? Gamma 2 comes up, and then I'm going to put a dotted version because it's the same place. It moves straight across here, but in the opposite direction. So this will be gamma 2. So let me draw those out. So gamma 1 looks like this. And our I is in there somewhere, not centered, right, because this thing's really tall. And then we have gamma 2, which looks like this. I'm making them separate even though they're not really separate. Yep. And then I's down here, so that's gamma 2. Notice that they share this common path. So if you go this way, but then you also go this way, those 2 paths cancel. So let's make a little note here that the integrals on these paths, so if you were to work out the path integrals, remember this, that if I have gamma f of z dz, and I flip the order on gamma, the direction on gamma, then I get the opposite integral. So the integral, the value from here to here is the opposite of the value from here to here, and those must cancel. So the integrals cancel on the shared path. Because opposite orientation. Opposite orientation. So this is a new trick. This is like the second trick I wanted to talk about today. So we're gonna rewrite this integral to look like something. We're gonna, like, first we're gonna do gamma 1, so this is equal to the integral around gamma 1, e to the z over z to the fourth minus 1, plus the integral around gamma 2. And now I'm going to do each of those separately. So let me give you a little time to think about that. But remember, you've got the factorization of z to the fourth minus 1.
So couldn't you also
Yes?
just use fractions to, like, you factor it out and put one fraction on the bottom of one fraction?
That's exactly what we're going to do. Yeah, but we had to split the curve first so that there was only one division by 0 per curve. Because if I left this single curve, then I had two problems. Cauchy's formula only works if there's one singularity inside the curve, that single W. So I need to apply it twice. But then what you're saying is exactly how we'll figure out what goes on top. And what will go on top will be different, and what will go on bottom will be different in each of those.
I was doing the partial fractions
Oh.
method.
Oh. Yeah. Okay. Yeah. That's also that would also work. Noah.
Okay.
Yeah. That
Just
would
wanted
be.
to make sure. 'Cause
I'll
like,
address that.
This isn't too different from what we've done before.
It's not too different. You're right though. You could do partial fractions. I'll do it that way in a minute. Did you already get the decomp?
I got the decomp for the reals and then the imaginaries because like that'll be easier, and then I can just cancel the real part instead of doing the thing that would actually be useful. And getting rid of putting the imaginaries in opposite ones, which would be useful but like slightly more difficult. So,
Yeah.
yeah. Anyway, I'm gonna do the easy way.
I don't know. They're both kind of some work. Both methods. You okay, Lou?
Yeah.
Okay.
Yeah.
So gamma 1 has the I in it. So the z minus I is what goes underneath here. And then on top is everything else. And here I'll just put z squared minus 1 because that encompasses both these. So that just makes that easier to write, and that's on gamma 1. This one turns out to be imaginary. I think it's pi I sine of 1. Negative. Okay, sorry. Is that what you were going to say?
Yeah.
Yes. Yes. But you got that otherwise?
Yeah.
Yeah. Cool. That's a weird one. There's pretty much one last example I want to do, but I don't want to push it out too fast. But I can set it up, and then you can think about how it might be impossible without this class. Well, actually, it's not impossible. I just thought this is a better one. We'll have fun. We'll have fun. What if I just put an X there? Yeah, let's make this a real one. Let's do Calc 1. Or Calc 2. Maybe that's Calc 2 where you put infinity up in the integrals, I think. Yes. Yeah. Nothing imaginary here. So let me stop. But can you work this? Let me just give you a few minutes. Can you actually work this through without using complex analysis? You get it? Probably is the answer, yes. It definitely is the answer. In fact, you might have seen the antiderivative somewhere today.
Yeah.
Yes.
Yeah, we could do that.
We can do that.
It's
What's the answer?
arctan
What's that? I forgot the word.
b minus negative b. Arctan of b minus arctan of negative b, then minus b approaches infinity.
Let's be really sloppy. Imagine we have like the extended reals. It's kind of that, right? Because the antiderivatives are arctan. Plug in the limits, subtract. What's the arctan of infinity? What does arctan look like?
If I'm remembering correctly, isn't it like U's, kind of like that?
Yeah, that's it. You're thinking of arc
I think
sine or arc cosine. Or no, you're thinking of secant.
Yeah,
Yeah,
that's
yeah. Secant or cosecant. So let's just review inverse functions. Why not, right? Why not? We need to know this stuff as math folks. Tangent, here's a period of tangent. But the whole tangent looks like this. Where's that asymptote?
90.
Yeah, it's 90 degrees or pi over 2, right? And then that just repeats. And wow, pretty bad. This function is not one-to-one. So it does not have an inverse. So we truncate it to the main period. And now it's one-to-one. So we restrict the domain between minus pi over 2 and pi over 2. And this now has an inverse. To find the graph of the inverse, flip it over the line y equals x. So to do that, or when you do that, these two strips become horizontal. Right? Like so.
So it's just pi.
Pi. This is pi over 2 minus negative pi over 2. Because as this goes out this way, so arctan of negative pi over 2, or excuse me, arctan of negative infinity is negative pi over 2. Arctan of infinity is pi over 2. And so this whole thing turns into pi. Looks like a complex analysis thing, right? Because it's got pi in it. Let's do a complex analysis. Because otherwise you're kind of forced to just know this. You need to know that antiderivative. And if that's a great thing to know, that's why we're reviewing it, because it's literally the most common antiderivative I've ever seen in my whole math career. Knowing this.
Really?
Yeah. Yeah. Like for real. Like arctangent, just knowing what arctangent looks like is going to save you endlessly throughout your math future. Know something about arctangent. It's everywhere. So, like, I don't think a semester goes by, no matter what class I'm teaching, where I don't need to know that picture right there. So, for us, here's what we're going to do. We're going to convert this into a complex integral. And I'm going to give you a fun fact along the way while we do this. So the first thing we're going to do, and I kind of hinted at this last Wednesday, is I'm going to create a curve that has a straight part on the real axis from minus r to r, and then it arcs back up and becomes a circle. So we've got this piece here, and then this circle centered at 0 of radius r, but just the top half of it. So I'll put a little plus, so it's just the top half of that circle. And this is our curve gamma here. So gamma is the union of the closed interval from minus r to r and that circle, that top half of that circle. You could even put a little sub r if you wanted, because it really does depend on r. Our goal is to just grab this part of it and hope that this part doesn't do anything, especially as we move out and let r go to infinity. So let's take a look at this. So our integral is going to look now like this. So basically the same integrand, I just replaced x with z, and I'm going to put gamma here. I can break this apart. This is actually two integrals. This is the integral over this part of the curve. So from minus r to r, 1 over z squared plus 1 dz, plus the integral over the curved part, the circly part. 1 over z squared plus 1 dz. Okay. So we need to know how this, in particular, this piece behaves as r goes to infinity. Because what we're going to see is that this goes to 0, the bigger r gets, this piece right here. So as r goes to infinity, this will die, and this will become the integral we started with. So let's take a look at a result. So this is a corollary of Cauchy's formula. Oh no, this isn't any of that. So upper bound on a complex integral. This is a formula in our book that they develop right after they introduce complex integration, but it essentially says this: that the absolute value of a complex integral over a curve gamma is less than or equal to the length of gamma times the maximum value of f on that curve. And now here I'm assuming that the max exists. So here I'm going to say f is continuous. This will be finite if f is continuous on gamma. So that helps me get an upper bound. That'll be something we come back to time and time again from here on out. So let's look at this guy right here. So let's check this out. So this integral on that top half of that curve, this thing right here, is going to be less than or equal to, how long is this curve? half of a circle of radius r, pi r. So this is the length of that curve. And the most this can be on that curve is 1 over r squared plus 1. And let me just put that up here, and then we can talk about that for a minute. In a minute. So this right here is the max possible of 1 over z squared on that curve. What is the limit of this thing as r goes to infinity? What is it? Sorry, what? Zero. Do we see this? We have an r to the first power on top, and r squared on the bottom. Polynomials, right? This bottom blows up faster than the top. That goes to 0. You can see that with L'Hopital's rule if you wanted. Lots of ways to see that. So, or just the one where you've got polynomial over polynomial. And this one has less degree than this one, so that the limit as you go to infinity is 0. If this is a smaller degree than this one down here. If they're the same degree, then the limit is the ratio of the leading coefficients. So this thing here, this is going to die out as r goes to infinity, just like we were hoping. Now we need to figure out what this is going to be, and this piece here is going to come from whatever value we crank out with Cauchy's formula over here. So now let's do this, use Cauchy's formula. Could you do that for me, please? Let's assume, since r is going to eventually become as large as we want, what is the trouble here? So imagine r is just a big enough curve to encompass any of the zeros here. What zero are we worried about? I. You all see that? That I is up here, and that as soon as r is bigger than 1, it's inside there. So using I as your W, could we just crank this up? And this is our last thing for the day. I have a feel. I thought we were going to be done with integration, but I have one more thing to say on Wednesday. You'll know you're right because we know pi is the answer. So Cauchy's formula should give us pi for the value of that integral.
Then I am correct.
Wait.
Yeah, I got it.
Yeah, you did. Yeah, perfect. You want a fun one, Noah, or not?
Sure, I'll take a fun one.
Yeah. I don't know if I'll do, maybe I'll just address this. I'll leave this. This is like between now and Wednesday if you want to check this one out. It kind of pulls together a couple things from today. What if we had, let's do this again. So you want to use the same game here as we did before. I'm actually thinking I said something maybe wrong over there, but that's okay. I'll talk about it. 1 over z to the 4th plus 1 dz. That one will take some work.
I'm just tempted to use. Oh no, I can't. No.
What were you thinking? What were you tempted to use?
Well, I was like, this is just the thing that is arctan times z squared, but it's not.
Yeah.
Would have been nice.
True. Does that make sense? This fact, yeah, awesome, awesome. If you, then you're getting it. So then this is going to be 2 pi I. This thing evaluated at I. And that turns into 2 pi I times 1 over 2I log. Yay, it's pi, we got it. Challenge problem, we'll call that the end of the day. I'm happy to walk around and talk to you about whatever you want to talk about, but let's try this one for challenge on Wednesday. Yes, sir.
I think I did it.
Oh my God, Jesus Christ. Let me see. Let me take a look.
Is it kind of rough?
Well, it should, so let's think about, this should be a positive answer because this is a positive integrand. And actually, sorry, make that an X, but yeah, it doesn't matter. But this has to be a positive number because it has, yes. So I look at the curve 1 over X.
It's just one equals I. There's one more problem because it's a different problem.
I don't think C equals I is a solution. Is a zero. Like that would have to have a positive area, so
Yeah,
we definitely expect a positive number.
I thought it was like the one that was just.
Yeah, this one's a little, this one's kind of a combo of 2 ideas from today. And you maybe are seeing what I'm getting at.
Yeah.
Yeah.
What were we supposed to make an X?
Oh, sorry, Grace, thanks. Yes, yes, ma'am. Both those things. Any Z up in that integral should be an X. Yeah, that one, I don't know. We'll see. This one could be pretty challenging, actually.
I'll figure it out later.
Me too. Me too. It might be brutal. I might be sorry I assigned this, but it's okay. We're all friends. You won't hate me for long.